Sean's our second talker for this session. I met Sean last year. He was a great mentor for my master's project. Sean received his PhD in electrical engineering from the University of New South Wales, Australia. He's currently an instructor at the Martino Centre for Biomedical Imaging, Harvard Medical School, and a research affiliate at Sales MIT. Previously, he was a postdoc at Stanford University. In 2016, he was a visiting researcher at Interdigital Communications San Diego. He received the APRS/IAPR Best Paper Award at DICTA 2018 together with David Taubman. Yeah, cool. Yeah.
Right, thanks for the introduction. And yeah, I just want to preface this talk by saying I'm not really a medical imaging person. So some of the things that, like Robin asked me, well, how does this work in OCT? I'm like, I have no idea, right? So having said that, I think there's always room in like science for people to contribute in different ways. And sort of that's what I hope to bring to the table today. So my talk is entitled Fully Convolutional Sliced Volume Reconstruction for Single Stack MRI. So basically, this is like a 1-minute version of my entire talk. So you have like a stack of 2D MR slices. Again, there are situations where you have to have acquisitions like this. And of course, this is a mostly axial scan, right, acquisition. And of course, if you look at it from this kind of view, then you don't really see anything. There's a partial volume effect, of course, but there's a lot of interslice motion, which means if you want to do sort of tackle further downstream tasks, volumetry and stuff like that, there's really no way to kind of make that work if you have a slice stack like this. So what I do is basically turn that into a reconstruct an underlying MR volume out of that. So that's so you can kind of switch off, and I guess you've kind of seen the entire talk. So I'll be breaking it down for you, of course, but that's basically it. And I mean, as a computer vision person, what better examples are than stereo disparity estimation, right? So in computer vision, there's this thing called stereo disparity estimation, where you're tasked with kind of trying to estimate the sort of the depth map given sort of two views of the same scene, right? So if I kind of go back and forth between the right and left views, this is sort of what it looks like. And of course, you can estimate from those two views a disparity field, which is 1 depth field like this, right? And that's possible because if you look at the epipolar sort of geometry, then what is the ray of light in one view is actually an epipolar line in the other view, right? So of course, now if you can kind of find the correspondence between, say, for example, this point here and this point here, which is actually seen as movement along this line, then you're good to go in terms of estimating disparity, right? And if you go 1 disparity estimating, that's your depth map, right? So why do I bring this up? Well, because sort of people were, so by people I mean deep learning people, were like, do we actually need those two views to estimate disparity? Why not just use a unit on a single view, right? And so this is called monocular disparity estimation or monocular depth estimation, where they try to go from one view to sort of the underlying depth map, right? And it turns out that if you just use like a standard unit to do this, then it kind of actually works pretty well. So, so what people have been able to do is kind of stuff like this, right? So you have like the scene, a scene that you want to estimate the depth field for, and if you basically throw at a unit a whole lot of these sort of single view disparity field pairs, then actually the unit is able to generalize to predict correctly the depth maps for unseen views as well, right? So, well, the joys of deep learning, yes, right? And so I looked at this, and this was kind of before I joined Martino's, right? So this was kind of very hot, I think, in Vlad and Colton at Intel Labs, his group, where he kind of pioneered some of these techniques. And I was thinking, okay, well, this is great, but then I joined the Machine Center, and then some of the people there and MIT as well, they were actually working on slice to volume reconstruction, right? Where basically the problem is to go from a stack of MR slices to like the underlying volume, right? And so I was thinking, okay, well, people are using multiple slice stacks to kind of piece them together into a MR volume. Can I actually do this using a single slice stack, the way that people are doing disparity estimation based on a single view, right? And so that's kind of what led to this research project. So like I was saying, like people doing fetal imaging, this is, they need this tech to work, right? Because, if you're trying to, take an MRI scan of like the fetus in the mother's womb, then obviously you can't exactly sedate the fetus or anything, right? And you can't tell the fetus to like keep still, right? So, but having said that, I'm not really a fetal person, and I kind of don't really care about, improving the quality of care for mothers, expecting mothers. I mean, I do a little bit, but that's not where I come from, right? And I was just very interested in solving the problem itself, because that's what computer science are known for, right? Like they think they're somehow better than the others, and then I think I can do this better, right? So I'm a little bit guilty of having that kind of mindset as well. But anyhow, that's how I got started on working on this problem. So essentially, what we try to do is to estimate or predict a stack of motion fields per slice from a single stack of 2D slices. And now that you have your motion stack estimated, you can kind of use that to warp your original stack of slices and sort of interpolate the result so that you get a nice 3D reconstruction like this. Right? So that's kind of the backdrop for this talk, and what I'm actually supposed to have started with is to mention that in high-resolution 3D MRI of subjects exhibiting severe uncontrollable motion, you kind of have to use something like FFSE acquisition to kind of freeze the motion and plane, and then sort of now you try to piece the MR slices together to form the 3D whole, right? So this would be my official introduction, but because I'm not a medical imaging person, I decided to go with the disparity one. Right, so if you have these 2D sort of based acquisitions, then this is kind of slice stacks that you end up with, right? So obviously this is an axial acquisition. So if you look at each of these slices axially from an axial view, then they look okay. But the moment you kind of step aside and look at it from the two orthogonal directions, they look, terrible, right? So what people have been doing using optimization is to basically acquire sort of 3 orthogonal stacks, right, slice stacks, and then they try to kind of put them together, sort of piece them together so that this is essentially the slice to volume registration thing that Ishvan also talked about, right? So it's exactly the same tech. They try to sort of harmonize the 3 different stacks so that you can have this 3D, so that you can reconstruct this underlying 3D volume, right? And so this is like a typical pipeline that most of these methods would use. So you acquire essentially sort of 3 orthogonal FSC stacks of single shot, fast, spin echo sequences. And then now that you have those 3 stacks, you would kind of sort of scatter all of the voxel data, voxel information into an original, a low resolution initial volume. And then now you kind of ping pong back and forth between, re-estimating the motion and refining the reconstruction until you somehow converge, right? I mean, all of this is a non-convex, non-linear problem. So you do this until you think you have converged. And now that you have an estimate of the underlying volume, you can super resolve it, right? So this is kind of the sort of the pipeline that most of these approaches use, right? And so many of these approaches work very well. I'm not trying to knock these methods, but they are iterative, and so you're using something like I guess conjugate gradients, I guess in many cases. So they are pretty slow, and these methods aren't things you can use during scan for like prospective motion estimation and that kind of stuff. So I think if I remember correctly, this methods like these this take maybe tens of minutes. I mean, depending on whether it's on CPU or GPU, I don't know, but it'll take minutes basically. Right. So, and this is another method from Alina Oos and others in 2020. And so again, it's very sort of flow chart driven, right? So have things converge, and if they haven't, then you kind of go back and okay, let's reinitialize the volume, and then so again, these methods can be pretty slow. And what happened last year was so at MIT, so Jun Xian, who has graduated now, his thesis was around doing all of this using vision transformers, right? So vision transformers, of course, he gets stellar results actually using vision transformers. But then if you have a look at this, there's a lot of sort of disjoint components here as well. There's the the sort of the transformer model that is responsible for estimating the motion parameters for each individual slice, as well as kind of another transform model that will estimate the volume. And then he kind of does this in an iterative manner where, again, you kind of take one step of motion estimation and then followed by volume estimation, and then go back to re-estimate the motion and so on and so forth. But then me speaking as a computer vision person, I was like, okay, well, can you not do this using like a fully convolutional architecture? Because so far I have not come across like a vision task where you can solve the problem only using transform models, right? So because it seemed to me back then like there's nothing between like very traditional approaches where you have to use numerical optimization and something that is on the bleeding edge, like vision transformers, right? Because the UNet has been sort of the mainstay of medical image analysis for many years now, right? So why is there nothing in the middle between these sort of two extremes, right? So that's when I kind of started to work on this. And so as a first step at making this fully convolutional, you might think, okay, well, let's just try to regress like a 3D volume against like the slice stack. Because if you stack the 2D slices together, it's kind of like a volume, right? So can you just go from a slice stack to a 3D volume and you have a UNet to do this, right? So it's like an image-to-image reconstruction model. And well, it turns out that it doesn't work if you do that, because if you think about the nature of these 2D slices, they're heavily motion corrupted, right? So so this is actually a registration problem rather than a denoising problem, which or a segmentation problem for that matter, which UNet is great for, right? So this doesn't work, and so we essentially, like I said at the beginning of this talk, we want to use something like a UNet to basically estimate the slice motion, and then kind of use that to do the 3D reconstruction. And yeah, so for that, we had to kind of go back to the roots of how optimization approaches work. And they essentially have, one thing nice about optimization approaches is that they have a really nice mathematical forward model, right? So there was a lot to learn from how these, what the forward model is, so that we can translate that into a fully convolutional setup. And so without having to understand too much about, there's not really much there. So if you have like say an underlying volume V, sort of that's like the unknown, right? Because if you had the V, then you wouldn't be doing any of this. So the forward model assumes that at time K, that volume V is rigidly, goes through rigid motion. And then of course, there's sort of an acquisition slice-based acquisition at time K, which is kind of like a convolutional process, right? So, depending on whether you're at time 0, 1, 2, 3, 4, 5, the slicing plane will kind of translate across the longitudinal axis of the subject, and that's how you end up with like a slice at time K, right? So this Fk is basically your 2D slice at time K, and V is the volume that we're trying to estimate. So in linear algebra, it's super nice, right? So basically, you just get this model where the underlying volume goes through some motion and then gets sliced. And if you stack all of these 2D slices together, then you get this F, right? Okay, so this is, although previous authors haven't really expressed whatever they're doing this way, it turns out that you can write whatever optimization approaches do as this kind of alternating optimization problem, right? So, so I'm not going to bore you with the details of these equations, but it turns out that probably the more difficult step is to estimate the motion of the individual slices rather than using the motion to reconstruct sort of the 3D volume, because I think Paul also knows this, right? Like all of this is very non-convex, but using the motion to reconstruct the volume is like completely convex, right? You just have to warp all these different slices using the estimate of the motion you have, and that you're done, right? So that's why we kind of realized that if we can go from a slice stack, regress a motion stack against a slice stack, then we should be good to go. And we came up with this splat slice unit architecture, which mimics the internal operations of these U and the V steps in traditional optimization-based approaches. We rolled it all into our unit. And so, of course, now, how do you train this thing? Then, well, so we would take the sort of synthetic training approach very similarly to what Eugenio and everyone else have been doing. And so at training time, you have access to sort of reference or ground truth 3D volumes, right? So you can kind of just come up with random but known motion to randomly kind of slice these 3D volumes up. And so now you have these ground truth motions and the sort of the slice stacks as a byproduct of the augmentations that you do, right? And then now if you can kind of use the motion stack as your supervision signal and slice stack as your input, then basically that's how you can train it. Except, what we know about convolutional neural networks is that they're pretty bad at just translating stuff, right? Because it's all convolutional, so it doesn't see translation, and it kind of also doesn't see rotations, right? Because, rotations, if you look at it at a very microscopic level, it's all very just translational, right? So we realized that getting our fully convolutional neural network model to stick things right in the middle of the field of view actually doesn't work, because it's just not capable of doing that. It's like you're in the deep in the middle of the ocean, and then sort of trying to ask yourself whereabouts am I? I mean, all you see are like waves, right? So you don't really see any landmarks or anything like that. So when we train these things, we just factor out sort of the global rotation and translation components of the difference the motion between whatever we have predicted and the ground truth motion stack that we're supervising all of this with. And of course, if you do all of this right, then the volume that you end up reconstructing actually looks like this, the flat volume. So it's got a whole lot of holes because remember, like the subject is moving along with the acquisition process. So for example, if the subject is moving at the exact same speed as sort of like how your TR basically, then you're going to miss out on a whole lot of sort of, you're going to have regions that are never captured, right? And in general, holes are like just an inevitable part of doing SVR. So, but what we can do is we can do self-supervised interpolation, right? So if we can have like another sort of pre-trained unit model that can go from a splat volume, so warped volume, using the motion that we predicted, to something that is closer to the underlying 3D volume, we can use that as an interpolator, right? So what happens is we do the motion estimation as a first step, and then using the estimated motion, we will have this volume that is warped, predicted. And then from the predicted volume, we go to something that is closer to the 3D volume by filling in the holes, basically. Right? And so these are the results that we get. So by the way, so although most of my customers, if you like, are going to be people doing fetal imaging, the one thing not so good about fetal data is the fact that they don't have ground truth volumes, right? Because unless you do it ex vivo, I don't know how that's going to work, right? It's just not going to work, right? So we started by testing all of this on adult brain scans. What are these? So Buckner 39, MCIC, all of these things. And these are this is the visualization of the results we get. So let me just show you. So let's start with this. So on the far left, you see the original slide stack. That's what I'm viewed. And so both of these are sort of satchel acquisitions. And if you do the splatting is just warping using the motion that we estimate, which is this column here, then you correctly sort of reconstruct the underlying 3D volume with holes, right? Because you're supposed to get the holes as a byproduct of doing this. And if you compare that to what you would get if you were to reconstruct these using the ground truth motion, well, that's sort of this third column. So they're very similar. And like the fact that you get these holes reconstructed faithfully to look like sort of the ones that you would get if you were to use the ground truth motion kind of gives us a lot of confidence that this is working. And of course, you don't want to give this kind of results to radiologists because they are not going to be happy with whatever you're giving them. So now if you interpolate across the missing regions, then you get something a lot nicer like this. So I guess in many cases, it might be hallucinating the pixel intensities in the missing regions, but remember there's actually, if you kind of step outside of this plane, then there's, the holes aren't actually that big, right? Because there's intensity data in the plane that is right in front of this and the slice that is in front of this and the ones behind it, right? So this is more like interpolation rather than in painting. And you'll see that whatever results we get after interpolation, they're pretty good approximations of the truth volume. And we did the same with fetal acquisitions. So I'll show you these two. So there's this public data set called FETA, which give you basically reference reconstructions. So we use that and we kind of just synthesized our own training data by slicing them up to train this. And of course, on the FETA data set, it kind of works perfectly, right? But now if you look at now on real acquisitions from MILE, so MILE is a different data set, And these are actual acquisitions, right? Even though the statistics of the motion are completely different to the kinds of training examples that we work with, they do a pretty good job at, our proposed method does a pretty good job at reconstructing the underlying volumes, at least sort of visually. I think this is sort of what you're supposed to expect, right? So, and we did a whole lot of kind of quantitative studies to compare our method with sort of the current state of the art, which is the work of that Jin Shen, the MIT PhD student who just graduated. We actually do a lot better. So our motion error is kind of basically half that of his work in this single stack setting. So, but yeah, maybe I should kind of just full disclosure. So he wasn't working on this single stack case. So he works with 3 or more slice stacks. So probably this method is not supposed to be used in this single stack case setting, but nevertheless, it's a very promising sort of result that we get. And but that's pretty much it. And I would like to just finish this by thanking all my collaborators and mentors and also NIA. So of course, I'm not getting support from NIA to work on field, right? Because that's the antithesis of aging, right? But yeah, I'm still funded by NIA as well as all of my mentors. Yes, thank you.
Emissions.
Okay. Are you planning to, so you are doing a fair amount of interpolation. Oh, okay, will depend pretty much on how well the images will align or not before when you have your stat volume. So you
yes.
have equations. Because this may be then later on used for volumetric analysis. It's also the intention to inform what parts of the image are interpolated.
Oh yeah, so I guess sort of, if you're giving this to radiologists to use, we have to basically sort of demarcate the regions that are interpolated, right? Because they don't want to look at it and they say, oh, okay. Yeah, because we don't want to be hallucinating anything, yes. But yeah, so that's sort of for radiologists' eyes, but I didn't show any of that, yes. You can mask these things out, yes. You're the chair, yes.
Well, sure, asking this question. So the question then is, in your case, you're being explicit about the case that you are hallucinating something. But isn't that generally the case for all of the methods that are being used on these applications? There's still, the misalignment of the data or the gaps in the data should be there regardless of the method that you use. So it's more of a general problem than something specifically for you.
Yeah, so I guess in practice, they will keep acquiring more and more slices until you sort of have a good coverage across the entire volume. But, so that's why the speed of the method is speed of methods is very important, because if it's going to take you 3 minutes to reconstruct a single volume, then you can't keep up with the speed of acquiring these slices, right? Yeah.
What sort of interpolator do you use? Because there are many different sorts that trade off support, with the blurring effect. So in your case, what have you found works well?
Yeah, so I got very lazy. So the interpolation you do, so there are sort of 2 components to this interpolation. So you have to warp your slice stack using the motion that you estimated, right? So that is you don't even need a fancy interpolator for that. We just use a box kernel, right, to just scatter the intensity information onto a single, what do you call it? Like a common volume, right? And then we use a CNN actually to fill in the holes after that. Yeah. And that is just trained in a self-supervised manner. So that kind of gets rid of having to, hand engineer like the Lansosh 3 kernels and all these things.
Any other questions? Are there any questions online?
Yeah, you're right. The workflow is the, oh, no, this is for Gentel.
I have probably one last question. Are you planning to use this methodology also to contribute to the problem of trying to have a super resolution?
Yeah, so Eugenio has this sort of basically, piecing together histological slices. So there, he had a postdoc who kind of used an optimization approach to, because there's no, if you're doing histological slices, there's no through plane motion. It's all in plane, right? So he had it a little easy, but yeah, there's plenty of other sort of opportunities to apply this to.
Can we get another round of applause?